pre-calculus students, this is Mrs. Marshall, and I am going to be going over today with you the section 1.4, and the rest of our chapter here and the last part of pre-calculus A, we're going to be covering a few sections of sort of some different aspects of function conversations. And today we sort of have, in a way, three different parts of talking about functions in sort of a unique way. We're going to start and kind of title this generic 1.4 section with building functions, as you see it in your note packet here. And building functions, we just got through doing a lot of work with the 12 basic functions and understanding all of the characteristics of functions. But we all know that a lot of functions that we have in our problems in day-to-day life and things that we do are not just the basics. They're usually a combination in some way, shape, or form of those basic functions, and we can certainly identify key characteristics of those. So today we're going to look at a couple of different ways that we can build new functions using a lot of those basic 12 functions that we just learned about. One of the ways for us to do that is to combine our functions in an algebraic way. So our first section here, combining algebraically, consists typically of the idea of, of adding, subtracting, multiplying, dividing, taking a basic function and kind of combining it in several different ways. So our notation that we use when we combine things algebraically is we tend to use sort of a very simplistic way of writing functions like this, where we have an addition of two functions, f plus g of x. Okay, and sometimes that f plus g is just kind of written there, but that would be a little bit vague, so it's more common that the f plus g is together in parentheses, and then the of x is additional in parenthesis piece. So we want to make sure that we understand this is still function notation. We are still referring to the g and f being added together as functions, but that the x is the input values. And so we can certainly then also do things like f minus g of x. We do f times g of x, f divided by g of x. Okay, and really these are the most common ones. Sometimes the f times g has a little bit of multiplication there. Sometimes it does not. But all of these types of notations are really considering taking two separate functions like f and g and combining them in a certain way. Without really going over examples of every single one of these, which I think that you guys probably can get the idea and understand that part. Okay, if I just do one simple example here and say most of your problems are going to be something like let f of x be x squared and g of x equaling out to, we could even say just 4x minus 7. Okay, we can certainly look at taking these and combining these in several different ways. So I could ask, what is f plus g of x? Okay. And we would know it and understand it. That's just basically taking the f function, adding the g function to it, and now this has created a new function. And this is certainly a function that we know and love, quadratic function at best. Okay, and it's just the idea of adding pieces and parts together of that nature. I could also do something like what is g divided by f of x, and that would just solely mean that I'm taking the g of x function and dividing it by the f of x function and creating a new function, also one that we've kind of seen and dealt with. So combining functions algebraically is pretty straightforward. Okay, when it comes to understanding the notation is really kind of the new part. And then one final little piece before we move down to the next section, just going to extend my page, is we are also going to ask you to identify some more domain types of answers. So for every one of those problems, the domain, we really just need to be careful to sort of follow with domains of the originals. Okay, so when we talk about the domain of, let's write this down here, domain of a new function, in general, I tell my students just be cautious of the domains of the old. So use the old domain and interpret new. It's kind of like a combination deal. You want to be really careful, okay, to realize that since you're using a couple of functions, if there are restrictions on those domains, then you need to carry those restrictions with to the new creation. But also, if there are some new types of domain restrictions, we need to incorporate those as well. So when we look back just above here at the couple of examples that I had, and I'll come back down there. So the original two f of x and g of f functions I have here, those domains would just be considered that negative infinity to positive infinity for both of those, because we don't really have any restrictions on that. And so if I now look to this new part, and I'll switch colors here a little bit, and if I say, okay, what about f plus g of x? What is the domain of that? Okay, certainly I'd want to consider the fact that my original domains were negative infinity to infinity, and then also consider what is the new function that I've created. Are there any additional restrictions on what I had there? And at this point, for this first example, I don't have any new restrictions at all, so I can be consistent to say that the negative infinity to positive infinity works. But for my g divided by f, now I have to realize that although my two original functions were both negative infinity to infinity, because I am dividing by this x squared with my new function, I'm going to have to take out that 0. So I'm going to have this negative infinity to 0 and then 0 to infinity as my domain. We've got to be careful that even though we've created a new function out of functions that did have an unrestricted domain, we need to restrict that domain. All right, so that's one way, okay, to actually put together functions to create new function is sort of what we call the algebraic route. The second way, right below this, is what we call composition. And composition is actually a fancy way to say that we're going to substitute one function into another function. It's a way to combine two functions by sort of eliminating or taking the domain of one function and putting that in as the new domain of another function. So the notation that we use to make this look different than the algebraic combination, and you should have sort of seen this in the past, but sometimes we don't use it all that often, is we talk about this f of g of x. F of g of x. I'm going to write that down here as well. F of g of x. Kind of a tongue twister here. F of g of x. And f of g of x simply means that, as you'll notice here, the g of x function is actually inside the f function. Okay, so the inside interior part of that, the g of x piece, has been replaced, that x part, with the g of x. And so this idea is that the g of x function is really getting put into the f function. G of x goes into the f function. Now this is definitely a different answer than g of f of x, because g of f of x would mean that the f of x function is going into the g of function. So we got to be careful because you're not actually going to get the same results. Okay, so this part, g, f goes into g. Whereas above, g goes into f. So I want to make sure that's the notation part. There's also a slightly different way to write the notation, and then I want to make sure that you understand what this means. So if you're at home watching this video right now, you're like, what is she talking about? Okay, so the other part that we have is our textbook has a slightly different way to say the same thing in here, notation-wise. So I'm going to just write both of those down, and we need to make sure that you are comfortable with both routes. Okay, and they mean exactly the same thing, it's just the way that they are written. So the f of g of x can also be written with a little o in between. So we have this notation, FOG, looks like fog. And when you look in your textbook, you'll see that also as the notation. That means the same as the f of g of x without the little O symbol. And of course, the g of x would also be similar, G-O-F, and then of x. Part of the problem that we have, just a little bit of a concern, is sometimes when we use this little mini O symbol, like you see here that I just wrote down, sometimes in this version or this version, students kind of make that O seem like it's multiplication, and so then they think it's F times G or G times F. So we want to make sure that we're very clear that that little O is that same idea of the of word here. F of G of X, G of F of X, and that little O is there. So when you make sure that you're looking notation-wise and the difference between those. Okay, and those types of notations are going to be equivalent. We'll use those interchangeably in class. Okay, they're used both ways in your textbook as well when you're working through your 1.4 odds assignment, so be aware of that. So let's also just wrap up this little section with an example so that everyone is clear as to sort of what this means, because not everyone has always worked with composition. So I'm going to go ahead and use a couple of examples here. We'll say f of x equals the square root of x, and g of x equals, let's go with x squared plus 2. And we'll use a couple of just some basic functions. So the idea behind this concept is that if I were to ask for f of g of x, okay, that means I'm taking the g of x function, I'm taking the entire function, and I'm putting that piece in for x into it. So there's the substitution idea. So the f of x, okay, concept is going to stay the main function, but I'm going to replace the x with the g of x function. You can kind of see where that g of x right here is sort of inside the f function. So you see how they are sort of relate to each other. You have the x part here, and then you have the g of x. I'll try to see if I can put those together here color-wise. And so because those are in the same spots, the idea is that I want to take that g of x function and put it in for the x. So that same idea of what function notation really means. That means that I'm going to go ahead and have a square root of, and then x squared plus 2. And that would be a composition, okay, of two functions. But on the flip side, one second here, I'll scroll as much as I can. The g of f of x is going to have a totally different look. You would almost think that they'd be the same thing, but they're not. Because this time, I'm going to take the f of x function and I'm going to put it into the g of x function. And I'm just going to take a minute here and sort of kind of erase all my arrows from before and rewrite stuff, just because. So we've got this g of x equals x squared plus 2 again. So now this time, for my second example, I'm now going to take this f of x function and I'm going to put it into the g function. And I'm going to replace the x and put the square root. So what I really end up having here is I end up with this square root of x squared plus 2. All right, now certainly we have some ability in some cases to simplify some work when we do composition. So this last example here, I know some of you are like, wait, isn't the square root of x squared? Don't those cancel out and just give us x plus 2? And that is true. So we can simplify, in some cases, the algebraic routes there. The reason that I put that step there is because the last little part that we have, similar to what we did above, is we've got a couple of restrictions on the domain that we need to be careful of. So we are once again going to ask you about the domain. And just like above, okay, when we talk about domain, we do want to consider our original functions as well as the new functions. The difference here just a little bit is what we want to do is we want to actually look at the domain before we simplify. So we're going to check the domain of the originals and before we simplify the new one. I'm going to put the unsimplified version. are any additional restrictions that we need to have on functions, we'll need to do that as well, just like we did before. But we want to be careful to not simplify first. Here's one of the reasons why. If we look at this last example, okay, our original two functions have a restriction here that the f of x function can only be positives. So as I scroll back up here, kind of like what we did before, and I'm sorry, this is getting a little bit crazy, a little bit messy, but the f of x function, its domain was basically 0 to infinity. G of x, its domain originally was our friend negative infinity to infinity. So that did not have any restrictions. But when I put things together, okay, and I look at what's new, even though okay, I have some restrictions on the originals, when I looked especially at this part here, if I were to just go all the way to the end and talk about what restrictions I have at the end, I would be missing the fact that I still can't have any negatives. And even though this is just straightforward linear, I need to understand that I really have to go back and look at the unsimplified version. So my domain for this second example is still going to be that 0 to infinity. Okay, I can't unfortunately take out the fact that those square roots and square cancel. I need to kind of consider those original functions and play along with that piece. In addition, when I look here okay, at the f of g of x, and I want to think about the domain there, okay, in this particular problem, because I have square root of something underneath here, and that underneath is never going to be negative, okay, I still want to keep consideration that that interior gut piece is a negative infinity to infinity, so I'm good to also have a domain here of negative infinity to infinity. So it's really sort of the gut that you need to be careful of. What is the domain of the gut? And then when you look at the domain of the gut, use that part with you and then add on any additional restrictions that might be there. So check for those. It's a little bit tricky. Just be careful that you're kind of always, as I say, look for the domain of the gut. All right, so now we spent some time talking about building some new functions, either algebraically or in a composition. Okay, if you flip to the next page of your notes, we're going to look at two other little parts. One of them has everything to do with what we just did, the other one a brand new topic. So this first thing on the back side is what we're going to have you guys actually do is work a decomposition. And a decomposition is working backward. Decomposing or breaking apart. So this decomposition section here that we have at the top of the backside is basically asking you to find functions f and g so that we have, in this case, an f of g of x. So g needs to be a gut, okay, and f needs to be sort of the outer function. And sometimes these can have multiple answers. So there's going to be a couple of times that I show you where you could have more than one possible answer. Sometimes there's only one way. What we do want to try to avoid is we'd like to have the gut g of x function not be just x. So we're going to look for g of x to not equal x. It's a little too easy and a little bit decomposition based, so we would like that function to be a little bit more. So here's what we're looking for in this first example, and I kind of have a little bit more of a specific breakdown here. But we can see in this h of x function that we sort of have some interior. So when we teach this to PreCalc, we look for, is there any type of function that's on the inside of another function? And that idea of the gut. And here it looks like there's this x plus 1 that's inside some parts. So that is an excellent choice for the g of x function, the gut. Okay, what is that particular gut? And then for the f function, what you want to do is just take those guts and remove them and replace them with just an x. That would leave me this particular function to be f of x, x squared minus 3x plus 4, and the gut being x plus 1. And you can always check your work to see if that works. If I take this g of x function and I plug it in for the x's, do I get my original h function? And the answer is yes. And this idea of a breakdown or a decomposition, okay, what I'm asking you to do is take apart my h function into its parts, okay, but not separating term by term, separating guts and outer functions. Okay, let's try just a couple others, and these other two that are right below here, I'm going to show you a potential couple of other options that you could do, especially for number 2. So I'm going to have an f of x need and a g of x need. So I usually tell students, start with the gut. Is there a gut that's on the inside of the function? And again, we have a fairly obvious 3x plus 2. Okay, sometimes those guts are in parentheses. Sometimes those guts are in absolute values or in under square roots. Sometimes they could be in denominators. Okay, there's a lot of things up in powers, a lot of places that we can find a gut. Once I've figured out what the gut is, then I take that out and I replace it with an x, and I should see the outer function. The outer function. This problem I could do just a little bit differently and still follow the rules of g of x not being x. And one of the things that I could do here, just to toss it, if you're like, oh, that totally makes sense, then disregard this other part. Okay, but just so you know, you could do this as well. And I could say, instead of using the entire 3x plus 2, I could actually decompose this by saying, I'm just going to let g of x be the 3x part. Okay, that still follows the rules that g of x is not just x. But if I make it 3x, then I could do x plus 2 quantity cubed. And I would still be able to say that this is f of g of x equaling out to h of x. So there's a couple of slightly different ways that you could do that. I would say more often than not, we're still going to stick with that first one that we did there. And here, number 3, I'll just draw a line. So this one, f of x equaling g of x. So again, once I'm looking for a gut piece, okay, and I'm going to go with that 3x squared plus x. And then if I take that out and just leave an x behind, then my f of x function is 2 square roots of x. And I could certainly do this one in a similar way to what I did number 2, but I could technically have the g of x function being the square root of 3x squared plus x, and the f function just being 2x. And that would also kind of work. But again, this one is probably far more the usual one, taking the guts out. Okay, so this is called the decomposition of a function. Decomposition. Okay, we're looking for that part. All right, this leaves us with one last topic that we're going to talk about here, called the implicit piece. So if you can follow with the last little part here, implicitly defining functions. Implicitly. This seems like kind of big fancy words, but actually what we're going to do here is kind of pretty basic. What implicitly basically means is we're going to break these apart, but in a special and unique way. And what I usually say is to break apart a non-function into functions. Okay, so we're going to give you a non-function relation, okay, one that we sort of know, one that we kind of understand to be true, and if we were to use our function test on it, it would fail the function test. Okay, and what our goal is to create 2 functions that actually are following the function rules, okay, that could be put together to create this non-function item. Okay, and I know it's kind of wordy, like what again? So let's look at an example because it makes a lot more sense with an example. Okay, so we just got through not too long ago talking about our friend the circle. And here's the equation of a circle. It's got a center at 0, 0, a radius of 3, and I'm actually going to draw just a little quick picture to help understand a little bit about what we're doing here in this implicitly defined section. So if I do a quick circle. This is going to not be real, well, not too bad, I'll be honest. Not too bad for a circle for our drawing here and our center. Now, because we have this visual picture, this is definitely failing the vertical line test. This is not a function. And not only are we failing that, but we also in our equation have a y squared, which was one of the no-nos of an equation piece for function definition. And so this is what we consider to be a non-function type of relation, like in our directions here. What we're going to do is break apart this equation into two pieces that actually are functions. And so what we're going to look to do is create some y equals functions, y equals. So your job is simply to get y by itself in this particular type of scenario. So I'm going to subtract x squared on both sides, and I get 9 minus x squared equals that y squared. And then I'm going to take the square root on both sides so that I get y all by itself. When I do that, though, remember not too long ago we had a conversation in chapter P about taking the square roots on both sides of the equation. And when I do that, I need to incorporate the fact that there's a plus or minus scenario. So with a plus or minus the square root of 9 minus x squared, okay, I have now actually created two separate functions. Okay, this is what we call implicitly defined. Okay, and I'm going to just sort of write those two functions down, starting to scroll a little bit here. Okay, so I have one function as the positive 9 minus x squared, and the other function as the negative square root of 9 minus x squared. By the way, a quick little note, you may not take the square root of 9 and the square root of x squared and get 3 minus x. That is a no-no. You may not square root parts. Okay, so breaking these into these two equations, separately, they are functions. They would separately pass the vertical line test, okay, and this is what the implicitly defined functions mean. Okay, is getting these two equations. And on my graph, not sure if this will help or throw anybody off, okay, but the positive square root would be considered this part. Okay, and so that would be this positive square root piece. The negative square root would be this bottom half. Okay, and so then if I define them separately, if you'll notice, if I only had the blue part up on the graph, it would pass the vertical line test. If I only had the red part, it would also pass the vertical line test. Put them together and they don't pass. Okay, this also gives us an opportunity, and I encourage you to do that. I'm not going to do that in the video today, but I would encourage you to take a moment and go into your calculator, your graphing calculator, and enter both of these blue and green or red parts, into your y equals in your calculator. One of them can be your y1. One of them can be your y2, and what will come up on your screen then is the graph of a circle, okay, with each of those two separate pieces, like you see the red and the blue in my picture. They don't often touch on the edges, okay, and that's just because of a little bit of restriction on the domains there, so it's very hard for it to be full circle this. But this breaking apart and getting two separate functions, okay, that would represent something that's a non-function, that's this implicitly defining ways. So you'll want to get y by itself, okay, and there's usually a positive version and a negative version. It's pretty common that you'll see y squareds in your problem, so work on a lot of square root pieces. Another popular thing is to have a y inside of an absolute value, or to have a function defined with a plus or minus in there. These are all ways that you can break apart two functions from a non-function part. All right, well, hopefully all of this has helped a little bit with some of that 1-4 section, and you are now ready to start in on the 1-4 odds. Good luck to you.